Hi, I'm Maxim, a multi-physics simulation engineer. I do thermal integrity checking of the PCB to ensure it's compliant with the system requirements. Although the PCB design at this stage is not yet complete, as soon as the board 3D geometry is ready, I can start the analysis in Simcenter FLOEFD, a CFD simulation environment built in X. Alex created the assembly file for the PCB design, so I can start the work from this point. First, let's do an arrangement of the assembly. To simplify the geometry for the FLOEFD solver, I'm using basic thermal models for some electronic components and exclude some other components from the analysis. These models can be built from the data available in the manufacturer datasheets. This decreases calculation time significantly while still giving accurate results. The FPGA dissipates around 100 watts, so I will add a heatsink with the integrated fan. The accurate fan geometry is not important for my simulation, so I replace it with a simplified version. I place the board into the chassis system design and will run the simulation in that context. This is not absolutely required, but the simulation will be closer to the reality when run out on real design geometries. I have already have the FLOEFD project created for this standard chassis we used in other designs. Some of the input data like computational domain, materials, fans, and other already predefined for the chassis. For this case, I set up the transient simulation project where the physical time is taken into account. Our chassis is designed to work up to 40 degrees. So this will be the operating temperature for this simulation to test the worst case scenario. I load the electronic thermal models from FLOEFD engineering database, a library, and finalize the project setup. The next steps are a mesh arrangement and solver setup, then I can run simulation. Once it's complete, I can display the results. There are different techniques in FLOEFD to do that. For instance, I can display the plots of the temperature distribution or fluid velocity. In the example, I display the plot to see the air velocity nearby the heatsink. It helps me to identify the areas in the design which may require the improvements. Now I check the temperature of the electronic components and the relevant chassis parts. As you can see, there is a significant overheat of the FPGA and adjacent DDR4 chips, so a better FPGA heatsink solution must be selected. The fan velocity and ribs geometry can be optimized. For the transient type analysis, I can create a video to see how the temperature changes over the time in accordance to the power load. In the example, I create the video to cover the process within the first 5 minutes of the load. Let's optimize the FPGA heatsink to get a better cooling. I can change the geometry without closing FLOEFD and return to the full assembly to rerun the simulation with optimized parameters. I increase the size of the heatsink, also adjust the volume flow rate of the fan in the FLOEFD project. Then run the simulation again. Despite some overheating, this looks much better. I can compare the results from the different simulation runs side by side. For instance, let's see the FPGA temperature compared from two different simulations where different heatsink size and fan were tested. I can see from the report the proposed heatsink optimization decreases the FPGA temperature by 20 degrees. I think certain adjustments at the chassis can improve the cooling of the control board further to meet the thermal requirements. I will work on that while the layout team continues work on the PCB. Adding the heatsink impacts the current PCB component placement, which must be fixed in the mechanical and electronic views of the PCB design. I will make the change in an X and alert my colleagues to adjust accordingly.